So remember last time we had this problem with an 800 Newton force like this. And if you number the members this way, the length of member 1 was 3 meters, and the mass of member 1 was 50 kilograms. The length of member 2 is 1.5 meters, and the mass is 25 kilograms. And what we've done so far is come up with the whole system of equations. So we did the rigid body analysis for each of these two members. Just as like a refresher, the rigid body analysis for member 1. Does member 1 have a fixed point? Yes. So from the rigid body analysis for something with a fixed point, how many useful equations do you get? One, that's right, just the moment equation. So that's one equation, and then we went to body 2. Does that one have a fixed point? No. How many useful equations do you get in that case? 2. 3. 2 for Newton's second law, and then 1 for the moment equation. So after we do that full rigid body analysis, we have 4 equations. And we have had 7 variables. And then the constraint equations were the requirement that these two members have the same acceleration at that pin where they meet. And then the requirement that the pin in the slot, that pin can't have a vertical acceleration because the slot prevents it. So those are our 7 equations, and they look like this. So 0.26 F12x plus 1.477 F12y minus 150 alpha 1 is equal to 3087.67. Then negative F12x minus 25 A2x is equal to 0. Then the third equation, negative F12y plus RC minus 25 A2y is equal to 245.25. Then equation 4 says 0.13 F12x minus 0.739 F12y minus 0.739 RC minus 4.6875 alpha 2 equals 0. Then equation 5, now we're on to the constraints. 0.260 alpha 1 plus 0.130 alpha 2 minus A2x is equal to 0. Equation 6 says 1.477 alpha 1 minus 0.739 alpha 2 minus AY is equal to 0. And then the last equation says negative 0.739 alpha 2 plus a2y is equal to 0, and this equation 6, that should be a2y. Okay, so there's our system of 7 equations for 7 variables. Everybody who has a calculator here, take a minute and see if you can get this to work out by reduced row echelon form, okay? I'm going to do it too, and yeah, better than this, but this is really the key to getting these. So we need a matrix that has 7 rows and 8 columns. That's the 8 columns. Seven rows. The rows are the equations. And the columns, you have to choose an order for the variables. I'll go F12X, F12Y, A2X, A2Y, RC, alpha 1, alpha 2, and then the last one is the constants. And so equation 1 says F12X's, we have 0.26. F12Y's, we have 1.477. Alpha 1's, we have negative 150. The constant is 3087.67. Remember, in your equations, the constants always have to be on their own side of the equation. If you don't do that, then all your answers will be exactly backwards. Okay? Equation 2, F12X is negative 1. A2X is negative 25. That's it. Equation 3, F12Y's, we have negative 1. A2Y's, we have negative 25. RC's, we have 1. Constants, 245.25. Equation 4, F12X, we have 0.13. F12Y, we have negative 0.739. RC's, we have negative 0.739. Alpha 2's, we have negative 4.875. Equation 5, A2X's, we have negative 1. Alpha 1, we have 0.26. Alpha 2, we have 0.13. Equation 6, A2Y's, we have negative 1. Alpha 1's, we have 1.477. Alpha 2's, we have negative 0.739. And then the last one, A2Y's, we have 1. And alpha 2, we have negative 0.739. And everything else is zeros. So that's the augmented matrix I used. And then just RREF on that matrix will give you the answers. Okay, before I move on from this one, I want to bring up the possibility of, so remember that you have to be given the angular velocities because Newton's laws don't let you calculate angular velocities. And that's not a deficiency, that's just the way nature works, you know. From forces, you can't figure out velocities. You can only figure out accelerations. Okay. So what if, okay, so it'd be nice if you're given this problem, and if there are going to be angular velocities, it'd be nice if the angular velocity of every body is given. Okay. But that's not necessarily going to be the case. In this problem, just giving an angular velocity for body 1 specifies the angular velocity that body 2 has to have. So you can imagine a case where someone's just like, oh, and we know that at this instant, body 1 has an angular velocity of -5 radians per second. Okay. So now, what if we're told that the angular velocity of body 1 is -5 radians per second? How would you figure out the compatible angular velocity of body 2? Yep.
Would it somehow have to be like proportional, like with the cross product with the like the radiuses?
Yeah, for sure. I mean, that's what's, it's kind of like just a geometry problem. But the way we're going to do it is we're going to require that, how did I number these? What was that pin there called?
B.
B. Okay, so what we know is that, and this was C, we know that the velocities of B according to member 1 and the velocity of B according to member 2 have to match up. They have to be the same, or otherwise this thing is flying apart and we're not allowing that. And we know that the velocity of C has to be parallel to that slot, meaning that the velocity perpendicular to the slot, the vertical velocity, is 0. Okay? So we're going to just write those up as velocity constraint equations, and we're going to solve for the variables that way. Okay? Okay, so I'm going to start with the velocity constraint at B. And just like with the accelerations, I'm going to calculate that velocity according to each one of these members. Okay, how are we going to calculate the velocity of B according to member 1?
Watermelon.
Yeah, well, the velocity version of watermelon, you know. Yes. So remember that the velocity of a point in circular spherical motion is omega cross r. Omega is 0, 0, -5. That was given. And r is the vector from the center of the circular motion to the point B. So what angle did we use for this?
We used 10.
Okay, yeah, 10. So, so that's going to be 1.5 times the cosine of -10 and the sine of -10. Since we're doing cross products, I'll put a third component in there. And so that's 1.477 negative 0.2600. So the velocity of B, according to member 1, is 0, 0, negative 5, crossed with 1.477 negative 0.2600.
We just found velocity of B to be 1 point. Why are you times that by the?
I just found the what?
It's that first equation.
Omega cross R?
Yeah.
Yeah.
That.
That's the velocity of B, right?
So why are you timesing that again times the?
Well, I just hadn't put the numbers in yet.
Oh, okay.
So now I'm just substituting in the numbers that we know for those.
Gotcha.
And this comes out to be negative 1.30, negative 7.3850. And now we'll do that according to member 2. But member 2 is a little more complicated because there's no fixed point, so we have to use relative motion. Okay, so we're going to use that the velocity of B relative to the ground is equal to the velocity of B relative to the center of mass of member 2 plus the velocity of the center of mass of 2 relative to the ground. So the velocity of B relative to the center of mass is omega cross R. Omega, well, we're looking for the value of that omega, so I'm just going to call this 0, 0, omega 2. And that's going to be a variable that's going to propagate through stuff. The R we know. This goes from the center of mass of 2 to B. So the center of mass of 2 to B is 0.75 times cosine sine of 10.
But why do you use positive 10 versus negative 10 on that?
Because this is a new body now, so you just have to think about what these...
Oh, this is member 2, so it's
right. So we're going from the center of mass of 2 up to here.
Okay.
And so that's 0.739, 0.1300. And so the velocity of B relative to the center of mass is 0, 0, omega 2, crossed with 0.739, 0.1300. And that is negative 0.130 omega 2 for the x component. For the y component, it is positive 0.739 omega 2, and then 0 for z. And now the velocity of b relative to the ground is just equal to this plus whatever we're going to call the velocity of the center of mass of 2. So I'll put that in as 0.130 omega 2 plus v2x. That's the velocity of the center of mass of 2. And then 0.739 omega 2 plus v2y, and then 0. Okay, so what the constraint says is negative 0.13 negative 1.3 negative 7.385 is equal to negative 0.13 omega 2 plus v2x, 0.739 omega 2 plus v2y. Can we solve this to come up with, all we're looking for is omega 2. Can we solve for omega 2? No, that's 2 equations for 3 variables. So now what are we going to do? Yeah, I mean, for sure we're going to, but just try to make it not too long because we got another step to do, you know? Well, there's nothing we can do with a matrix yet. We have 2 variables for 3 variables and 2 equations, you know? But what we can do now is there's one more constraint that we know, okay? There's one more velocity constraint that we know. We know that this point C cannot move up and down. So the y component of C is 0. Okay, so now we're going to go to the velocity constraint at C. So we'll hold these for now. And we're just going to keep moving on. Go to the velocity constraint. At C. Well, there's no fixed point on body 2. So the velocity at C relative to the ground is equal to the velocity at C relative to the center of mass plus the velocity of the center of mass relative to the ground. And this looks very familiar. The velocity of C relative to the center of mass.
Is the ground in this case the wall, or is the ground like down?
Yeah, the ground always just means something fixed in the coordinate system. Okay. So it's the wall in this case, yeah. Just anything that's fixed in the coordinate system. So velocity of C relative to the center of mass is omega cross r. The omega vector is still 0, 0, omega 2. That's always true for a whole body. That's not a point-by-point thing. And then that r vector is just going to be the opposite of our r vector before. But the r vector is going to go from the center of mass to the point C. So that's, 0.75 times cosine and sine of 190 would work. Or you can just take the opposite of what we just did here. So negative 0.739, negative 0.130. So the velocity of C relative to the center of mass is 0, 0, omega 2 crossed with negative 0.739, negative 0.130, and that is positive 0.130 omega 2 for the x component, negative 0.739 omega 2 for the y component, and 0 for the z. And so the velocity of C relative to the ground is equal to, according to relative motion, it's equal to this plus what we're using to express the velocity of the center of mass. So that's 0.130 omega 2 plus V2x, negative 0.739 omega 2 plus V2y. I'll leave out the z this time. Okay, so now that's an expression for the velocity of that point C. What's our constraint, though? Why set y equal to 0? Yep. So the constraint says negative 0.739 omega 2 plus V2y is equal to 0. And so now we have a system. Notice that this isn't the cleanest system of equations, but we have two equations there, one equation there, three equations for three variables, and we can solve it. So our first two, I'll write this as negative 0.13 omega 2 plus V2x is equal to negative 1.30. And our second equation says 0.739 omega 2 plus V2y is equal to negative 7.385. And our third equation says negative 0.739 omega 2 plus V2y is equal to 0. Okay, so now you could use reduced row echelon form to solve this. It looks like actually this wouldn't be too bad to just solve by substitution, but I'm going to plug it in.
So just to clarify, these three equations would replace the last three equations from that.
No. This would be like this is, the whole problem that we did was assuming that omega was equal to 0, that this thing is instantaneously at rest. So now we're saying, what if it's moving, and what if we're just told, like, you can tell that you can tell just intuitively that being given an angular velocity for member one is enough to fully define what's happening with the system as far as angular velocities. But that doesn't mean we have everything immediately that we need to plug in here, you know? And so what I'm doing now is saying, if we're told that member one has a clockwise angular velocity of 5 radians per second, how do we figure out what the angular velocity of member two is? Okay, because it's totally defined by what this is, just the way that system works. But it's not obvious looking at it what that relationship is. Okay.
So this is just kind of bonus info. I'm just trying to figure
Yeah,
out. in the work-
it's bonus information, yeah. I definitely will not make you do this on a test, possibly on a weekly assignment. That would be the only way I would assign something like this.
in the workflow.
Yeah. Okay, so,
Do we still have time for solving number 6?
no, sorry.
You do 12 to 2, right?
What?
You do 12 to office hours, right?
From 11 to 12 today.
Okay, thanks.
Okay, so I'm going to do omega 2, V2x, V2y, and the constant. For equation 1, omega 2's, we have negative 0.13. V2x, we have 1. Constant is negative 1.30. Omega 2's, for the second equation, we have 0.739. V2y's, we have 1. Constant, we have 7.385. Omega 2's, we have negative 0.739. V2y's, we have 1. Constants, we have 0.